Hey guys, so let's solve this problem. This problem is related to the concept of static equilibrium. In this problem we have a 3-meter long ladder that leans against a wall, and the ladder makes an angle 60 degrees with the floor, right? You have to find the minimum value of the coefficient of static friction that will prevent the ladder from slipping. Okay, so we have to make sure that the ladder doesn't slip. In other words, it stays in static equilibrium, it stays still. And we're going to assume that this the contact between the ladder and the wall is frictionless. Okay, and we have to apply, so if you have studied the static equilibrium, you should know that when you apply the conditions of static equilibrium, we make sure that the net force is 0 and the net torque is 0. Okay, so we have to apply these three conditions on this ladder. We have to make sure that the net force is 0, okay, in the x direction, in the y direction, and the net torque has to be 0 as well. So these three conditions will give us equations that will solve this system that we have over here. Okay, so let's redraw this. Let's draw the ladder over here. Okay, here's the ladder. Okay, now there is normal force over here, which we're calling N1. There's a normal force here, N2. Okay, there's static friction over here. Okay, there's no friction over here. This is frictionless. The wall and the ladder. Okay, it's frictionless, and then there's the weight of the ladder. So these are the forces acting on the ladder. This is our x direction, this is our y direction. Okay, now let's apply the first condition. The first condition is that the net force in the x direction has to be 0. Okay, so pause the video and think about this question. So what are the horizontal forces acting on this system? Okay, so you can see that N2 is horizontal, Fs is horizontal. Okay, so and N2 points towards the positive x-axis, and Fs points towards the negative x-axis. So the equation you get is N2 plus N2 minus Fs is equal to 0. So N2 is equal to Fs. That's your equation for the y direction. Now let's look at the this is your equation for the x direction. Let's look at the y direction. The net forces in the y direction has to be 0 as well. Okay, so you can see that the forces in the y direction are N1 and W. So that's easy. So you get N1 minus W is equal to 0. So N1 is equal to W. Okay, so these are your two equations from the condition that the net force have to be 0. Let's call this equation 1 and this equation 2. We're going to use these equations to solve the system. But there's one more equation, as we discussed in the beginning. That equation is from torque. The net torque has to be 0 as well. So net torque is equal to 0. Now this is a tricky thing. So let's call this angle theta. We know this angle. The question gives us this angle as 60 degrees. Okay. So if you go back to the video, if you saw the video of torque, where I introduced torque, I discussed two methods, right? We're going to use the second method, in which we extend the line of action of the force, okay, and draw a perpendicular. And even before that, we need to first, when you want to calculate torque, you have to first decide on a pivot point. The pivot point, when an object is static, it's not moving, the pivot point is your decision, okay? You can decide a pivot point anywhere you want. You can decide it here, 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 or even over here if you want to make your life harder, right? But the pivot point, the object is static independent of the choice of your pivot point, okay? So the easiest choice in this case is actually this one, okay? And if you go back to the video, I said that any force whose line of action goes through the pivot point produces 0 torque, right? So these two forces will actually produce 0 torque if you choose the pivot point over here. So it's always a smarter choice to choose the pivot point, so that you get rid of some forces and the torque is then really easy to calculate. Okay. So we just want that if we choose this as our pivot point, okay, P, then we just need to calculate the torque due to this guy and this guy, okay, and we're going to use the second method to do that, okay. Now in the second method, if you go back to the video, we said that we're going to extend the line of action of the force, and we're going to draw a perpendicular, right, so that we can get this distance, right. The second method, remember, the torque was r perpendicular times F, where our perpendicular is this distance, okay. So we always want to draw perpendiculars from the line of action of the force to the pivot point. So we extend the line of action over here and we draw this perpendicular. So we need the length of these perpendiculars in order to get this r perpendicular for each of the forces, right. So the torque, right, there are two forces, a torque due to W plus torque due to normal force N2 is equal to 0. I'm going to plug in the plus and minus when I plug in for torque, okay. Now you have to decide which one is positive, which one is negative. So if you rotate around the pivot point, what I do is I rotate my finger around the pivot point. You can see that the torque due to weight is counterclockwise, okay, anti-clockwise or counterclockwise, and the torque due to the normal force is clockwise, okay, it goes along with the clock. So you want the torque due to weight is therefore W multiplied by R perpendicular for W, and the torque due to normal force is clockwise, so this is a negative sign, and normal force 2 multiplied by R perpendicular for the normal force N, okay, this is equal to 0. Now getting this perpendicular distance, once you know that this distance, right, you want this distance, then you have to use trigonometry to get this, right. So the length of the ladder, right, the length of the ladder is given as 3 meters, right. So the length of the ladder is known, let's call it L, okay. Now the weight of course acts at the center, so this distance is L by 2, right. So let's draw it over here. So you have this weight acts over here, right. So this distance is L by 2, right. So this is your right triangle. See, this is theta, you know theta, right. So you should know what this distance is, because you're looking at this right triangle. So this is L by 2 cosine theta, right. And if you want this distance, you will look at this big triangle, right. We want this distance and this distance, okay. This distance and this distance. So this is L sine theta, okay. Again, we need this distance because it is the moment arm of W, and we need this distance which is the same as this because it is the moment arm of N2, okay. So therefore we get W times L by 2 cosine theta minus N2 times L sine theta equals 0, okay. So let's further solve this. You get W times, so the L you can divide off by L, right. The L cancels out, so you get W by 2 equals L, and if you divide by cosine on both sides, you get L tangent theta, and N2 times tangent theta, okay. So N2 you can write as N2 is equal to W over 2 tangent theta. Now you can use equation 1, okay, use 1. This is our equation 1. This is the equation for N2. So N2 is equal to static frictional force, okay. So Fs is equal to W divided by 2 tangent theta, okay. Now in order to prevent the ladder from slipping, we want the static frictional force to be maximum, okay, so that the ladder doesn't slip, okay. So Fs is equal to Fs max. We want Fs to be equal to Fs max, okay. So Fs is equal to mu s times So Fs is connected with this normal force, right? Fs is equal to mu s times n. Okay, where this is the maximum, right? And this static frictional force, right, is equal to mu s times, so normal force, and the normal force is equal to the, yeah, we have to use this equation. Let's call this 4, right? So let's call this equation 4. So then we'll use 4, okay, use 4, and we'll plug in what is Fs, right? Fs is equal to W over 2 tangent theta, okay, and we'll also use 2, and 1 is equal to W, okay, so 4 and 2, so W over 2 tangent theta is equal to mu s times W, okay, so the W cancels out, the weight of the ladder cancels out, okay, and you get mu s is equal to 1 over 2 tangent theta. Okay, so that's your answer for the static frictional force. Okay, if you want a condition, if you would like a condition on like an inequality, then you can write this as like Fs is less than equal to, in general, Fs is less than Fs max, right? So in general, so you get Fs less than this, and then you can plug that in, you get this, and then you get mu s is greater than equal to this. Okay, okay. So the minimum value, or that of mu s, this is mu s greater than equal to 1 over 2 tangent theta. So the minimum value of mu s that you want is you now you can plug in that number, and theta equals 60 degrees. So for theta equals 60 degrees, you can plug in that number, and mu s turns out to be greater than equal to 0.29. So for the ladder to be in static equilibrium, the minimum value of mu s is equal to 0.29. Okay, that's what we want. So if we take two surfaces with this value of mu s, okay, with this relative value of mu s, then you can get the ladder, a 3-meter ladder in equilibrium, and you can see, interestingly, it's independent of the weight, right? Yeah, mu s doesn't depend on the weight. So so this was the problem of the ladder in equilibrium, in static equilibrium. And you can see, again, quickly, you have to first, let's quickly review it. You have to first apply the conditions of net force in the x direction equals 0, net force in the y direction equals 0, net torque equals 0. You then apply each condition. Each condition gives you an equation. So we get this 1, 2, and then this equation, right? Yeah, this was our third equation. So we get these three equations. Then we solve them together, okay? To get a condition on mu s so that the ladder stays in equilibrium. Okay, so this is a demonstration on how you would apply conditions of static equilibrium. So hope you like the video. If you have any questions, post them in the comments, and please subscribe.